I would like to take this opportunity to thank everybody that is joining us today for this webinar. The topic today is going to be hosted primarily by Jorge Garcia, one of our support specialists. Jorge has been working with EAGLE for, I would dare to say, a little over 10 to 11 years or more. He has been hosting a series of signal integrity webinars as well, and we asked him to see if he wouldn't mind hosting this webinar about high-speed PCB layout designs. He has hosted this several times for multiple universities, and I just thought the topic is very interesting and would be of much use to our other friends. So I'm going to go ahead and stop sharing my screen and let Jorge take over. Thank you again for joining us, and have a great day. We'll be right back.
Okay, check. Can you guys hear me?
I hear you just fine, Jorge, right now.
Okay, I'm sharing my screen. Let's see if it
looks good.
Yeah, and YouTube caught up already. Okay,
yeah.
So we're good.
Yeah, don't get confused here. They lag a little bit. So.
Yeah, I just wanted to make sure. Does the audio lag on YouTube as well?
Yes, it does.
Okay.
Yes, it does.
All right, cool. So let's go ahead and go into this presentation. This is one, like Ed mentioned, that I've given for different universities, and really the key thing to keep in mind with things like this is that what makes it maybe hard or a little bit scary is just not being aware of these types of effects and things that can come into play when dealing with high speed. It's not really that in any sense it's super insanely difficult. It's just that it's a wide array of effects that you have to be aware of, that they exist and they can affect your design, and which ones have impact in the specific situation you're working in. So depending on the circumstances, maybe one of these things is not as critical as another. And being able to make that judgment calls where experience and obviously studying and learning about these topics comes into play. So the first thing we want to mention is about the realities of power supplies. Okay. When you're working with real world power supplies, they're not perfect. They don't have infinite output impedance. So whereas in SPICE, if you think about it, the assumption in SPICE is that whatever you set the voltage rail, that's what it's going to be. You can have circuitry, and sometimes if you ever do this experiment, if you put a dead short or you put a resistor with like 0.00001 ohms, because you can't have zero because it'll be a divide by zero error, but you put a really, really small value, you'll get current in like millions of amps, and it's still 5 volts. It's still a perfect line. That's not reality. Depending on your application, if you have, for example, an FPGA board, FPGAs are known for sucking up a lot of power. You're going to have dips, you're going to have sags. Your 5-volt rail may become 4.5 volts because it can't supply the amount of current, or it may become even less. So these are the types of effects we want to be aware of. When you get that 5-volt regulator, make sure that you're aware of what its current limit is. Because if you start drawing more from it, you're going to see that voltage start to drop. Or other things may go wrong with the regulator. So why are we talking about our voltage rails? Well, the first key topic in high-speed layout is bypassing. Okay? Any active components, your operational amplifiers, your microprocessor. If you ever look in a high-density BGA, there are many coupling capacitors, tens, maybe even hundreds of decoupling capacitors, okay, of different values. This right here is just a very basic rule of thumb. If you have nothing else to go off of, a 0.1 microfarad capacitor can help. Okay, but having these decoupling capacitors as close as possible to your active circuitry is going to help keep the voltage rail stable and make sure that you don't get any weird erratic performance. Okay, now what do we mean by weird or erratic performance? Basically stuff that you can't explain. If any of you do software, if you've ever had, if you've ever programmed a microcontroller and your stack overflowed, That's what we're referring to by erratic behavior, just complete nonsense that you can't figure out why it's happening. One of the things you may want to check is your decoupling capacitors. You want to make sure that you have good solid rails that are stable at your circuitry. And again, in high current situations where you have, maybe an FPGA is doing a lot of processing, your decoupling is vital. The circuit probably won't function without the decoupling capacitance. So keep that in mind. Now, taking it a step further, when you see a capacitor, okay, in your mind, especially if you're going to do high-speed layout, you need to recognize that it's not just a capacitor, okay? Real-world components aren't perfect, okay? And you're going to hear me reiterate that as we go through this presentation. In the real world, the most realistic approximation of a capacitor is actually this type of RLC circuit, okay? Those of you who have ever done power supplies, you know that electrolytic capacitors have an ESR, have an equivalent series resistance. It hurts voltage ripple if you have a high ESR value on the capacitors, and it can make other effects. You'll also see that because it's a series RLC circuit, there's a frequency at which the capacitor no longer behaves as a capacitor, but rather becomes an inductor and no longer decouples the circuit. So that's why you're going to see that in sensitive circuits or circuits that cover a wide range of frequencies, you'll see multiple decoupling capacitor values recommended. Okay, and having multiple capacitors in parallel has a few advantages. Number one, your overall equivalent series resistance gets lower because you have these resistors in parallel. And number two, you can make sure that the impedance is low across all the frequencies of interest, all the frequencies in which noise could couple into your circuit, or where you could have some sort of failure. So that's something to keep in mind. Now, you don't have to figure this out on your own. Whenever you get a component, the manufacturer almost always gives you a recommended base layout, what decoupling you need, how many. So you can use that as a starting point. Depending on your application, you may need more, but it'll get you in the ballpark. Okay, so it's not something that you have to worry too much in the sense of having to figure it out. When in doubt, always throw, the rule of thumb, the 0.1 microfarad capacitor, but always refer to the data sheet in case there's a more specific decoupling recommendation. And again, as your circuits work with higher frequencies, the more decoupling you're going to need, because you need to make sure that that voltage rail is clean across all the frequencies that may affect your circuit. Next point is what constitutes a high-speed signal, okay? If you've been in electronics for a short time, you probably think of wires as just wires, as interconnects, point A to point B, but you don't think about them as something that can affect your circuit, that can affect its operation, okay? There's a threshold where you need to start thinking of wires and interconnects as a part of your circuit, where you need to take into account how they affect the signal as it moves through your circuit. Okay, where that threshold occurs defines what constitutes a high-speed signal. Okay, so if we look here, you'll see that in this graphic, if you're past that threshold, if you're dealing with high-speed signals, then now all of your wires, all of your interconnections, you have to treat them as a transmission line. Okay, it has a signal path, it has a return path, which all signals do. But when you're in lower frequency regimes or with simpler signals that aren't moving quickly, then mentally we tend to kind of ignore the return path. But the reality is you do always want to be aware of it and whether it applies or not. Okay, so when do we run into this threshold? How do we define it? Okay, you'll notice here I've put a simple definition. Different people will define it differently. It's not a set black and white threshold. Okay, so there's a realm there where it's a little bit gray, but just know that if you meet any of these criteria, you need to start being careful. You need to start being aware of what's going on. So if we look here, we give an example. You need to figure out what's the highest frequency the design is going to be dealing with. If your traces are longer than about 1/10 the wavelength of that frequency, then you need to start worrying. Then you need to start looking at if you need to model your interconnects as transmission lines. Maybe you need to model some of them and not all. Which ones do you need to model? So look at this example. Okay, and what you're going to notice is that the absolute frequency of the waveform isn't a critical thing. The rise time, whatever the fastest rise time in your design is, that's really what's going to determine what's the fastest frequency you're dealing with. So if we look here, this could be let's say this is a 10 hertz square wave. Okay, 10 hertz, really, really slow. You might think, I don't have to worry about it. But when you look at the rise time of this is, let's say it's 100 nanoseconds, which is actually fairly slow also. In high speed, you may run into, 1, 2 fractions of a nanosecond. But let's take this value of 100 nanoseconds. We figure out frequency as the inverse of the rise time. We get 50 megahertz. Okay. The speed of propagation, how quickly your signals move through your circuitry, is the speed of light divided by the square root of the relative permittivity of the material.
George, would you mind zooming in just a little bit on that? Because
Yep.
on YouTube, we can't really read the letters too well.
Thank you. Thanks for the heads up, Ed. So what we see here is we can make the basic assumption that we have FR4. If you are doing super high speed stuff, you will likely be using different materials that are tailored specifically for the application. But just as to get some numbers, to get some intuition, FR4's relative permittivity is 4, hence the name, I think. I don't know exactly if that's why they named it FR4, but it's a good way to remember it.
Works for me.
Yeah. So as we can see, square root of 4 is 2. So the speed of propagation in a circuit board is half the speed of light, roughly. So the wavelength of a 50 megahertz signal in your board, if you notice here, we do the math, works out to be 3 meters. So 1/10 of that would be 30 centimeters, which works out to about 11 inches, I think. 11 inches or so, roughly. 12, so it might be like a foot. So if you have traces longer than about a foot, you would need to start worrying about treating your interconnects as transmission lines, because at that length, they're starting to interfere with the propagation of your signal. And again, this is coming from the guidelines specified by TI. Different companies will use different thresholds, will use different parameters. They're all kind of in this ballpark, though. Some may say 1/10, some will say 1/5, some will say, some will just use the time, the rise time in nanoseconds. So if you're longer than so in nanoseconds, I always find that definition a little confusing because you're turning length into a time. But this one works for me. And this is what you want to keep in mind. So you make this calculation, you have any signals that are longer than that, then you need to worry. That longer than 1/10 of that. Otherwise, you can treat everything just as a really simple wire. And for most of the stuff that hobbyists may do or people may do on a personal level, you can usually treat everything as just a wire. And that's why we progress. We get to progress initially in electronics, so we don't have to worry about these effects and taking them into account. So as a quick recap, the key point to remember from all of this discussion is that you want to keep your traces as short as possible. The shorter you can keep them, the further away you are from having to treat them as a transmission line. So you get lower noise coupling, lower losses, improved signal integrity, lower chances of an accidental antenna on your board. So the shorter you can keep the traces, the better off you'll be. And that's really the key takeaway from this. So we're going to go now into the next topic that we want to cover. And this is about impedance matching. So one of the first things you learn in electronics is the conditions for maximum power transfer. So in order to be able to deliver power efficiently, to get the maximum amount of power across some sort of connection or wire, the impedances need to match. Okay? So yes, if the impedances match, you'll probably have half the voltage at the other end, but the amount of current times that half of voltage gives you maximum power transfer. That's the absolute most efficient transfer of power that you can do. Now, there are other things that that arise, or other consequences that come from maximum power transfer. It's also the cleanest, most distortion-free way to transmit a signal. So what ends up happening is, if you pretend that you're a signal walking along a trace, the thickness of the sidewalk, let's say, should be constant. Okay, if you're walking down the street and you're on the sidewalk, you're walking comfortably. If all of a sudden there's a roadblock or a change, now you need to move, you need to adjust your position, you need to maybe bend around an obstacle. So all of that makes it difficult to continue. So with the signal, what ends up happening is your signal's looking for a constant impedance. As long as impedance is constant, it maintains its shape, everything is good. The second it runs into a difference of impedance, you're going to see reflections. So part of your signal is going to bounce back, and that's going to create distortion. If enough of your signal bounces back, besides losing power, you're getting additional distortion in the circuit. And the exact reason is kind of beyond the scope of this webinar, but just know that whenever you have that change of impedance, your signal is going to distort. The degree to which it distorts is dependent on how big the change is. So if you just have a small change in impedance, it's not going to distort much. If you have a very big difference in impedance, it's going to distort a lot. And that's what we're seeing here. So if you notice, we have this transmission line, and we're going into an op amp. Now, if the LM741 here is just for illustrative purposes. I know that a 741 op amp is horrible for anything remotely close to high speed, but it's just to indicate an op amp. Okay, this is a preferred way. ZO equal to ZL, you get a nice clean signal at the op amp. If you just take it straight into the op amp presents a very high input impedance. So you have transmission line. Typically, transmission lines are designed for the application to have a certain characteristic impedance. The most common is 50 ohms. You'll see 75. In some applications, there's 300 is also a standard. But definitely 50 or 300 going into a million or 2 million or more. That's a very big change in impedance. And that's going to create a lot of distortion in your signal. And that's what we're going to see here in the next slide. Oh, I skipped a slide, I think is what happened.
I think this is one of the first times I see Eagle being used as a PowerPoint.
Yes, it basically is a PowerPoint. That's true. So if we look here, and yeah, I did skip a slide. You can see what ends up happening. At the entry of the transmission line, you have a signal. If the impedances match, you will get pretty much that same signal. Obviously, if it's a voltage signal, it'll be at half the voltage, but it'll have the same shape. It'll be clean. If you have a big mismatch, like in going into an op amp, as we've shown before, those reflections will create distortion. Now I've drawn this dotted line, kind of treating it as if this were going into like maybe a comparator or some sort of digital circuit. And you can see that the distortions, or the wiggles, as we'll call them, are getting close to that threshold. Imagine that if you have so much distortion that they start crossing, they go beyond it. Now you get these errors in your data, because you're getting highs when it shouldn't be high and you're getting lows when it shouldn't be low. So you'll start getting misreads in your data, and that can cause a circuit to completely not work. So that's something that's very, very critical. If you're dealing with, especially like high-speed communication protocols, RS-485, USB, all of that, you want to keep that in mind. You want to terminate your signals. You want to make sure the impedance is uniform. And in doing so, you can guarantee that your data is going to arrive properly across all your interconnects. So even if it's something that visually looks short to you, you know, you have let's say an inch-long trace. If you're running USB-C, 2 millimeters could cause an issue if you don't account for it right. So you want to make sure to be aware of the requirements of the protocols you're using. The final thing we want to talk about is grounding. Okay, and I use the term kind of just because it's a common term, but we do want to be careful once you start thinking about high speed. You want to think in terms of a signal path and a return path. All current flows in loops, right? So if it went out, it has to come back. If you just think of something as ground, you're kind of thinking of ground as like a big plane, an infinite pool where all the current goes into. That's not 100% true. Well, actually, it's not true at all. But for simple circuits that aren't at high speed, it kind of works. And that's why a lot of people get confused when they start working into more precise or high-speed signals, that you can't treat ground as ground anymore. You can't treat it as an infinite sink of current, because it's not. When your current flows into a ground plane, it's actually not just dispersing evenly through it. It's actually trying to follow the closest path that it can back to its source under the signal path. So you and in other webinars we'll cover that. But basically in the ground plane, return current tries to be as close as it can to the original signal current, tries to follow the trace from which it came. So with that in mind, let's talk about these different grounding arrangements and why sometimes they can be beneficial or why they can cause difficulties. Okay, so in this one, in the schematic, they're all represented the same way. But if we go to the board, you'll see that the way they're implemented is very different. So here we have a daisy chain grounding arrangement, which is considered bad. We have a star ground, and then we have the plane. Okay, star grounds and planes are considered best practice. Daisy chains are always considered bad, even though in simple circuits it does work just fine. And in many circuits it works just fine. But what's the problem with this? Let's go to the next. Okay, when you do a daisy chain, what's going to happen is that because they're all in series, the resistance or the impedance of those trace segments sums as you go along, which means that the voltage or the return voltage here is different than the return voltage here, is different than the voltage here. So all of these in our minds ideally should be at the same voltage. They're not. They're not all ground. This is some voltage higher than this one. This is a greater voltage than this one, and so on and so forth. Okay, in an extreme case, this can cause a circuit to not work because you don't have a good reference. The star arrangement is better because you don't have a summation of resistances. Even if these are slightly different because they're all small, you can see that the voltages here, here, and here are all about the same. And that allows the circuit to work better. That avoids any differences in your ground levels. A plane kind of affords the same idea. A ground plane is a wide area of copper, so you don't have these large impedances that may accumulate. Whereas if you do a daisy chain, you may have these really thin traces, and if you have high current, then you have losses. But because you have a wide plane, you don't have to worry about losses or traces restricting current flow. But you still want to make sure that when you're dealing with this, that you have clear areas for the current to return back to their source. And that takes us to our final slide over here where we talk about plane separation. Okay, so this is a kind of a little bit of a controversial topic in the sense that if you do it wrong, it could actually create worse issues for your circuit than if you just had a big continuous plane. But the idea here is that, let's say we have our circuit. Okay, we have digital. Digital circuitry tends to, again, a very broad stroke here, tends to be considered noisy because you have clocks. Clocks are square waves. Square waves have a lot of harmonic content. If they're going really fast, which they typically are because we're dealing with microcontrollers or FPGAs, then you have a lot of harmonically rich current going into the return paths. Okay? Analog circuitry is very sensitive. It's easy to corrupt, especially if you have low-level analogs. So if you're doing like medical equipment where you have very small signals you're trying to measure, all of the harmonically rich return currents are just going to destroy your analog signals. You're just going to be so corrupted with noise that it will be very hard to extract it. So in some situations, it may be beneficial to create separate planes for the analog and the digital sides, or the analog and digital circuitry. The idea here is that all of the return currents will stay in this digital plane and not interact with the analog plane. Okay, they won't jump over. What can happen if you have a very complex layout, if you have the analog near the digital, there can be some intermingling of those currents. And that increases noise and that creates signal integrity issues. So this is considered one valid way to remedy it. However, if you do your layout very carefully, you may not have to create the split. You may not have to create the two split planes. What you can do is, if you do the layout carefully in such a way that all the digital is maybe on one side and all the analog is on another, they won't intermix because the return currents are trying to follow the same signal path in order to minimize losses and impedance, because electricity, like water, looks for the path of least resistance, or in the case of a high-speed design, and more generally, the path of least impedance. And that path occurs when the return current can follow the same path through which it came, to the signal path. So if you have a trace going to a component on the top layer, and you have the plane on the bottom, the return current is going to try to follow that trace on the top. It's going to try to be as close to it as it can. But that's not always possible to create that separation. So in those situations, the next best thing is to have split planes, and they only overlap at a single point. They have to overlap, but they only do so at one point, and that's near the power supply. Okay, so that's what we wanted to cover today. I'm sure there's lots of questions. So let's get to it.
Thank you, Jorge. That was a really, really good information. Getting somebody on YouTube, Foxy's like, yeah, good advice. Ooh, I like that. Oh, he's about to work on some USB designs. So, and when it comes in regards of using impedance matching,
Mhm.
is a really good advice. So we're going to go ahead and open up the platform to any questions that anybody has on our friends. You could use the Q&A or just use the chat, and we'll go ahead and take care of those for our friends on YouTube. You're more than welcome to just put it on the chat that is live as well. I'm trying to monitor both of them. If you have any questions or comments in this regards, go ahead and place them now. In the meantime, I'll go ahead and put in our email address in case you wish to contact us after the webinar with any questions as well. But we like to do the questions live here because it might be questions that maybe somebody else hasn't thought about and can use this information as well. So if you, as someone said once before, the only bad questions are the ones not asked.
That's right.
So don't be shy. You have any comments or questions? Wow, we got a really nice attendance on the live YouTube stream. A lot of people really join us. Very nice.
Any plans to release new tool for length matching? The meander command covers length matching pretty well. You would, the only thing we would want to do is something that could do the impedance calculation, because then you could do a more accurate impedance match. If the width of the traces, their whole length is the same, and they're the same length, then you can typically, it's a bit of a simplification. You can say that their impedance is matched as well. However, if they separate a lot, or things like that, then there's a little bit of impedance change there. But pretty much, if there's no change in width, then as long as the lengths are matched, you have a very good approximation of impedance matching. If for some reason you have to change widths, then that's where things kind of go off the rails, and that's where an impedance matching tool would come into play and would give a more accurate result.
Yeah, we saw a pretty impressive design not too long ago.
Yeah, we can't say squat about that. So,
but but it was very impressive though. We have somebody on YouTube. His is a bit more on the aesthetic side of things.
uh-huh.
But he's saying,
Did I draw something ugly? Is that what
I
he's
guess
saying?
my main question would be about ground and analog ground and using the right symbols for them.
Mhm.
G and D seems to be common.
So what you can do, Eagle, if you look in the supply 1 and supply 2 libraries, you're actually given several different ground symbols. There's GND, there's AGND, there's DGND. I think there's a few more as well. Basically, you can use whatever you prefer. It's whatever convention, as long as you're consistent, then you'll be okay, because Eagle will define each supply symbol as its own net. So you have to be careful that you don't have, for example, two different supply symbols in your library called DGND, for example. Because what's going to happen is, because they have the same device name, even though they look different, they're both going to be connected. So that's the only thing to be careful with. But by default, in supply 1 and supply 2, we don't have that situation going on.
Yeah. Now, Jorge, there's been instances that I've done support, and the users will attempt to actually have an analog ground and a totally separate ground used for digital on the schematic itself, and join them on what one point in common within the board layout. Is it really that necessary to do it that way, or could they just run with ground with the same name and then just position them in the appropriate place on the board in groups?
You can do that, and that does work. I think mentally it's a bit more taxing, but it is the most ideal way. If you can maintain the continuous plane, that's preferable to having to do split planes, because now you don't have as low an impedance to that reference plane. But they're considered about equivalent, although it's slightly better to be able to have a continuous plane.
Okay. Okay, very well. Now we also have somebody on our Zoom saying, is it possible to do length matching of segments of this for the same net? For example, with DDR3 flyby topology.
It is possible. What you can do is, in the meander command, you can specify a length. Because what's going to happen is, by default, the meander is going to look at, if you have a pair, it's going to look at the larger of the two and set that as the length to match to. However, if you're doing a single net, for example, what it'll show you is just the measurement of the net, and then if you input a length that's greater, then it will add meanders. So you can length match any net actually in your design. You just have to enter a length to match to. And that's very easy. When you click on the meander icon in the command line, type in what length you want it to match to, and then it'll insert the meanders.
Also, if you're using differential pairs, it will actually give you the value of the primary, and then also it will give you a percentage of how much are they matching between each other as well. That's only working on differential pairs.
How much do things change when adding multiple layers, 8 to 12? It depends on the signal you're routing. As you know, a signal can be considered basically a microstrip in the simplest case, where you have a ground plane underneath a trace on the top layer. As you add layers, if you're going to maintain the same thickness of the overall PCB, the individual layers thin out. So the impedance changes because you have a change in distance between the plane and the trace. So in the general case, adding multiple layers is going to change the numbers a bit. So you do have to be aware of it if you're trying to match some exact value. If you just need consistent impedance profile, then that becomes a little bit less
You know,
extreme, or less important, sorry.
we have Brunel. I think we kind of answered it, but I think we could rephrase it. It says, how do you handle split planes or separate grounds if you are on a multi-layer board? Don't you just do that by layer usually?
Usually it's best if you can dedicate the entire layer
Yeah.
to a plane if you can. For cost reasons, that's not always possible. So in those situations, you'll have to do the split plane thing. But basically, you just grab the whole, you grab the polygon command and you track the outline of the board. Or if you're on the newer versions of Eagle, just right-click the outline of the board, convert to polygon, select copy, and then pick what layer you want the polygon to be, and it'll match the outline of your board exactly.
And it will keep a distance according to what you have set on your DRC, just to let you know.
Yep.
Now, one of our friends over on YouTube, Jorge, he says, he made, it's kind of more of a comment. He put, could you prepare a webinar in practice? How to calculate necessary impedance and how to design PCB. I'm thinking about a PCB for UHD signals. I guess he's using ultra high.
UHD, is that like a ham radio?
What
Or
type of, so Claude, if you don't mind telling us, giving us a bit more specifications to your question on, and this is one of our friends on the YouTube channel.
because we do have webinars coming up that are a bit more practical, because this is just an overview, but where we analyze a bit more in depth the different parameters of signal integrity. So like transmission line calculations and things like that are coming up.
Yeah, I have scheduled a series in regards of, I don't want to use signal integrity, but signal
Right.
quality,
Correct.
signal quality series for Eagle. So just continue to follow the control panel, our social media, or just visit our website where we put the schedule there as well. Now we have another question on our Q&A. Jorge says, in my design, 12 volts is dropped to 5 volts using a buck to 3.6 volts LDO. It is necessary to isolate it. Is it necessary to isolate their ground/apply plane? 3.6 volt is used for a 4G communication module.
Ooh, really nice question. Okay.
Very good question. Extremely.
So this is something that's good to talk about. In the case of the first stage where you have the 12 volts being dropped down by a buck regulator, okay, that's a switching regulator depending on the frequency at which it regulates. Typically, a switching regulator nowadays is 100 kilohertz and up. What you want to be aware of is a lot of people think that when you look at the data sheet of a linear regulator, which is what you have following it to drop it to 3.6 volts, a lot of people assume that the power supply rejection ratio is going to take care of any noise that comes prior. What ends up happening is when you look at that data sheet, you'll notice that most linear regulators are set up to have a good rejection ratio at line frequencies. So at 60 hertz, 60 to like 120, 150, in that area, you have really good power supply rejection. But when you go beyond it, any frequencies higher than that basically come through. So any noise that your regulator, your switching regulator has, and again, I don't know the exact frequency you're running your buck regulator at, but I'm assuming it's 100K and up, that noise pretty much just gets through your LDO. So with that said, if you're using a communication module, the communication module is going to have its own filtering circuitry on it, so it's likely not an issue. If you have a good 4G communication module, which is what I'm assuming here, they've built in their own filtering, their own things to make sure that the power that they're getting in is as clean as possible for their purposes. So your 3.6 volt rail is probably fine, unless you tell me otherwise. But keep that in mind. Just because you put a linear regulator in front of a switching regulator doesn't mean your power is coming out clean. The ripple from the switching regulator is most likely coming in unaffected through the LDO.
Excellent. Thank you, Jorge. Appreciate that. That was a really good question. Can't say his name. He posted as anonymous. So that was actually a really, really good question. We greatly appreciate it. Um, so, Claude wanted to give us a clarification that he was referring to Ultra HD uses and the LCD displays. That's what he was referring to.
Oh, okay. Thank you. Thank you for clarification. So, Ed, remind me, what was this question again?
The question was um, how to calculate necessary impedance and how to design PCB, thinking about a PCB in a Ultra HD uses and LCD displays.
Okay. For the LCD display, again, it's going to depend on the type of driver that the LCD display uses. So you're going to want to reference the data sheet for the display you're trying to work with.
The power up. Mm-hmm.
Um, but for sure, there's definitely high speed signals there. There's a lot of data that has to move very quickly. So definitely you're going to be very concerned about your signal quality and making sure that your lengths are well matched and all that.
I guess
So
this is somewhere in HDMI levels
correct. It's that type of
or
connector. It's
higher.
the
Uh-huh.
type of, because if it's Ultra HD, I'm thinking like
Mhm.
4K.
Yeah, exactly.
And even 1080p is non-trivial.
Hmm.
1080p is a very fast signal. So I would recommend checking out the data sheet of the LCD you want to incorporate into your product. See what type of layout the manufacturer recommends and try to stick as close to it as you can.
Excellent. Thank you, Claude, for participating and posting your questions. We greatly appreciate it. I don't see anything else in Q&A except how do you handle split planes? Oh, we already
Yeah,
did that.
we answered that one.
Yeah, we already answered that one. Well, I don't see any new questions. Everybody, I've been able to provide everyone on our YouTube as well as on our webinar platform our email address for the support channel. The recording of the webinar will remain on the YouTube channel for a little while. One of our producers will eventually edit it and post it again. But this was really, really good information. Jorge, as always, thank you very much. Greatly appreciate it. We got one more question just creeped up just really quick from one of our other friends says, in one slide, why did you mention the up voltage at V over 2?
The output voltage,
The
yeah, the reason
voltage divided by 2.
the reason I mention it over, it's in this one. Okay, I think he's talking about this right here. The reason is that when you do this maximum, because for a lot of people, what they're used to is working with a voltage signal. Especially when you're getting started in electronics, almost all the signals you're ever dealing with are changes in voltage. So in that context, we're taught that you want to have low output impedance and really high input impedance, because that way the voltage doesn't drop, when you're transmitting it, because that's the signal of interest, voltage. But when you're dealing with maximum power transfer, which is more critical because you want to maintain the quality of the signal, you have to, in your mind, get used to the idea that the voltage that's arriving at V out is going to end up being half of the voltage that you put in. And the reason for that is that you have matched impedances. The impedance of the transmission line and the impedance of your load, if they're matched, it's basically a really simple voltage divider with the two resistors being the same. Hence, your output voltage is V over 2. And I just mentioned it because a lot of people, that sounds funny to them. Like, why wouldn't I want maximum voltage across? And the reason is that the signal you're interested in isn't necessarily voltage. Is you want to make sure that you have the maximum power transfer, because that maintains the quality of your signal going through. If you're dealing with audio, doesn't matter. You're dealing with 20 kilohertz signals at most. Your interconnects are transparent to that. But that's why I mentioned it, just because many people, when they see that V over 2, are like, why would I want that? That doesn't
Mhm.
make, and that's why.
Well, you just want to let everybody, thank you, Jorge, for that. Really appreciate it. Hopefully that took care of your question. I just want to inform everybody that is here that part of us will be at Santa Clara on September 10th at the exhibition for PCB West. If you're in the area, it'll be great, a really good time. We usually run a really exciting booth, and hopefully you can join us and identify yourself. That way we could exchange some ideas and say hello to you. So thank you very much. Okay, so I think we're good. Everything has been answered. Jorge, as always, amazing work, great preparation, and the idea of using Eagle for my power slides, I think I'm all in. So I'm all in on that one. So thank you, everybody, for joining us. Appreciate it, and have a great day.
Bye, everyone.